So one of the things as volcanologists that we're supposed to do is forecast when eruptions are going to occur. Forecasting what's going to happen at the end of the story. When's it going to happen? And if you have a nice simple volcano like this, with a magma chamber 10 kilometers deep, and a simple volcano, and say there's some earthquakes down here, we think magma's on the move, we know that magma is rising at, say, 10 kilometers an hour, we know the volcano is going to erupt in an hour. Easy job. But volcanoes tend to look a bit more like this. There's not one simple pathway. There's not even one magma chamber. There's actually a whole series of pathways in magma chambers, which makes it fun to be a volcanologist because I get to tell lots of exciting stories and there are lots of possibilities. But it does mean that eruptions are hard to forecast. And the other question we're asked as volcanologists is, what's going to happen? How big is the eruption going to be? And so there's a whole range of different eruption styles you can have. Coming out the top of your volcano, you can have booms, throw lots of ash up into the air. And you can have splats and lava flows that are a bit more runny. Or of course you can have geothermal energy. So it's up to us to try and work out which one of these things could potentially happen. So you are going to be tested. Normally I don't get this many people turning up to my classes, so I'm quite chuffed. But yeah, I'm going to be asking you questions, and that's why you've got the cards in front of you. So just to recap, ash goes boom. It's generally from cooler, stickier magma with lots of gas in. Lava can flow or go splat. And it's from hot, runny magma, which isn't so gassy. So a lot of what we've learned comes from experiments. So I have a lot of fun labs here in New Zealand, and I work with people abroad where we do experiments. And yeah, they're fun, and you learn a lot, whatever age you are. So I'm just going to show, so remember, this is going to be on the test. So we're starting off with the lava lab here at the University of Canterbury. So I have this rock that some of you have seen. So this is a bit of homemade lava from the lava lab here in UC. And you can see it gets pretty hot in the lava lab. So this is 1350 degrees C. And we literally melt rocks, and we keep those rocks hot and runny by maintaining those high temperatures. And this gives us the ability to make lava by keeping the magma hot. Okay, so now it's time for your cards. So you've all got cards with letters on. And the first question, start off with an easy one. So, lava needs to stay hot to become a runny lava flow. Is this true or is this false? So raise A cards for true and B cards for false. Okay, that's looking pretty good. Most people have got A. We've got a few rogue people out there, but most people have got A, and it is true, right? We want to make lava, we need nice, hot, runny magma. Okay, so now, here is me in my spaceman suit in Hawaii, and I've just scooped a bit of lava out of a lava flow, and you can watch that lava gradually cooling. As it cools, you start to form crystals in it. Okay, so you can cool down and you can crystallize, and you can actually change the composition of magma, okay? So, a magma without much gas that is cooler and crystallized might make A, geothermal energy, or B, lava. Okay, this is kind of a hard question, and we've got a bit of a mix here, okay? We've probably got about half and half, okay? So what I'm getting at here is, remember, for lava to come out of the volcano, it needs to stay hot and runny. So what I'm getting at here is, for magma to stay underground, it needs to crystallize. So I was going for you guys to answer geothermal energy, because we wanted to keep that magma underground and not let it erupt as runny lava, okay? Wouldn't be fun if you got it right every time. You wouldn't learn anything. Okay, so we've also got a lab where we can put gas in and out of magma. So gas is another really important thing. You've got temperature and you've got gas. And so we've got the magma brewery at UC. And in the magma brewery, we can actually pressurize magma, and we can dissolve gas in it. And then you can decompress the magma slowly, and you can grow bubbles. So that's like a little bit of magma popcorn, bubbles growing in your bit of molten rock. So this is getting gas into your magma, okay? So which of these eruptions needs cooler, sticky magma, but also gassy magma? Okay, again, we've got a bit of a mix, okay? So, gassy magma is this rock here. Anyone know what this rock is? Pumice, okay? It's pumice. It's pumice, it's got lots and lots and lots of gas in, okay? And it comes from quite a sticky magma, okay? So, and big boom eruptions, this actually came from Topor, so big boom eruptions are from gassy, sticky eruptions. Something like this, that looks suspiciously like a cow pat, without the smell. This is from a splat eruption. And you're right, you do need a bit of gas for a splat eruption, but you also need it to stay hot and runny in order for it to form a splat, okay? So everyone's clear? The answer I was going for here is big boom eruptions have gassy and sticky magma, okay? So hopefully we're learning something here. So you can also lose gas. And I can do the same experiments in my magma brewery, where we can heat up our rocks again, and instead of growing bubbles, you can see the bits shrink, because they're actually losing gas and the bubbles are coming out of it. It's densifying, okay? So you can lose gas as well as gain gas. Okay, so which of these eruptions do you think needs cool, sticky magma that's lost most of its gas? Okay, raise your cards again. Okay, looks like we're learning something. We've got lots and lots of B's here, so that's good. So small eruptions have less gas in them than the big boom ash eruptions. Okay, so another thing that is incredibly good fun to do is popping balloons in with high-speed cameras and letting the bubbles make a splash. So this is actually, well, also I won't give the answer away. So if we watch this video, if you burst a balloon, let the bubble hit the surface, it makes a splash, okay? And if you get stickier and stickier fluid, so this is now quite a sticky mud, you can start to create cowpat bombs flying through the air, okay? And you can vary the stickiness and make different size and shape bombs. Learn more about how volcanoes erupt. Okay, so which of these needs hot magma that splashes when a bubble pops? The big boom, the lava, the splat, or the small boom? Yeah, I can see lots of red. It's like at a rugby game. Yeah, so the answer is splat. You can make those lava bombs when a bubble pops at the surface and ejects those lava bombs out. So another thing we can do is in Germany, they have an amazing machine where they can actually decompress pumice fast enough to generate ash, and not only generate ash, you'll see what else they can do. So I work with these guys quite a lot. This is back in the day when dyed blonde hair and Hawaiian shirts were in fashion. Okay, so let's watch the video. So this is a pumice that's now decompressing, and all the gas is rushing out, and it's turning that pumice into ash. And the ash particles are now flying out the top. And can you see what that is? Micro-volcanic lightning. Like, how cool is that? This was a surprise. So the lab was not intending to make lightning. They just got better and better high-speed cameras, and they discovered that they were making mini lightning bolts in the lab, which is pretty cool. And if you've ever seen some of these spectacular kind of National Geographic style videos of big volcanic eruptions, you get lots of lightning. So explosive decompression. So which of these needs gassy magma to decompress and create ash? Big boom, lava, splat, or geothermal? Okay, it looks like we've got mostly A's, and that's the answer I would go for as well. Big boom, okay? That's where you need that explosive decompression to create lots of ash, and that kind of eruptions. Now here's another very cool experiment that my friends do in Liverpool. So you can also get earthquakes associated with volcanoes. And my friends in Liverpool have just discovered that when an earthquake occurs in magma, and you create a fault, and this fault slips against each other, an interesting thing happens. So now we're spinning two rocks against each other, two volcanic rocks, just like the friction that's occurring during an earthquake. And you can actually create magma. So you can see, rub your hands together, it gets hot. You can actually create magma this way. And we've learned that not only do you create magma, you can actually create a few bubbles in that magma as well through this process. Okay, so which of these needs an earthquake to create friction in a gas poor, cool magma that can still cause an explosion? Big boom, small boom, splat, or geothermal? This one's a bit harder. You can confer with your friends. You're allowed to. You can phone a friend. Okay, so we've got a bit of variation, but looks like we've got a mixture between B's and D's. And yeah, I would go with B's. You're getting these small boom eruptions. You can generate these small eruptions from friction. You can get small booms associated with geothermal energy, but it's not usually that kind of from friction generating melts. And this is a relatively new process. I could probably ask this question to the top volcanologists in the world, and most of them would get that wrong, so you're doing pretty well. And this is another test we do. So we have cores. You'll see cores like this, and you can squash volcanic rocks. And as you squash a volcanic rock, the rock can't take the stress. So this is an experiment that we can do both at UC and in Liverpool. And this is a core being squashed. And you can see, boom, as it squashes, it eventually fails. So which of these needs the compression of a relatively gas-poor cool magma to cause the rock to shatter? Okay, looks like most people have worked out by process of elimination that we haven't talked about sideways boom yet. That is exactly correct, and you could kind of imagine that thing was shattering out, out towards you. Okay, so from doing these types of experiments, we learn, we can develop equations of when things happen, and from making observations about what happens at the volcano, we can put this together into a model. But it's still quite hard to know which way. No model can really predict a complicated situation like this with all those different possibilities. So this is where our drill hole into magma could come in handy. So if we had a window deep down into a magma chamber, and we could sample a bit of that magma, we'd know a bit more about it. We'd know if it was gas poor, we'd know if it was hot, right? This would help us work out what's going on. And this is, it looks like a comic book, okay, but this is actually happening now. So there are a series of governments around the world clubbing together to try and build a research facility to drill into magma. And this is some associated material that we're developing for schools as well to help school kids learn and get excited about this project. Still haven't secured all the funding yet, so if we have any millionaires in the room, come talk to me afterwards. Okay, so now it's time to meet Rua. Rua, the magma brewer. Rua is the creation of Janina. Say hi, Janina. Janina's our volcano artist. So Rua is going to go on a journey through the Earth, and you are going to be scientists. Your job is to try and guide Rua